Alright, this is the second part of the Test 3 material, week 7 and 8. I'm starting with question number 12 this time. The latter part of this homework set deals with a binomial distribution. So remember, the binomial distribution takes in three arguments, n, x, and p. When we put them into either the binomial PDF or the CDF, the way we put them in is n first, then p comes second, and then x. So on this particular question, this is the PDF because this is asking for exactly 2. The 6 goes in first, then the p, 0.45, and then the x. Alright, so the probability of exactly 2 is 0.278 to 3 decimal places. Alright, now, as we make our way a little further, they're already given us the binomial distribution here. Remember, we can verify that this is the binomial distribution for n equals 5 and p equals 0.147 by just putting in the first two numbers into the PDF. If we only put in n, which is 5, and p, which is 0.147, and don't put in a specific value, then we get the distribution that they're showing us here. Right? The 0.4516, 0.3891, alright, 0.1341, 0.0231, 0.0020 to 4 places, and then the last one, remember e to negative 5 means there's 4 zeros, but since the next one is a 6, 8, and we're rounding to 4 places, it would round it up to a 1 there. Alright, so that's the PDF. That's what they're doing over here. They're just showing you, I got the binomial PDF, or the distribution by using the binomial PDF. We could have verified that easily. Now, all we're wanting to do here is refer to this display and come up with what's the probability more than one subject experiences headaches. So more than one, what satisfies more than one? 2, 3, 4, and 5. So we're just adding up these 4 probabilities here. So I'm going to throw this into a table because it's easy to do that stuff in Excel if they give you the table. Alright, so again, what's the problem asked for? More than one subject. So 2, 3, 4, 5 are the things that satisfy this. So I add up these probabilities and I get 0.1593. Alright, now another way that I could have done that just as easily, instead of just adding these 4 numbers up, is just to recall, what do these 6 numbers have to add to? They have to add to 1. So just as easily, instead of adding the last 4 numbers together, I could subtract the first 2 numbers from 1. And if I subtract those first 2 numbers, what am I left with? I'm left with the sum of the other 4 numbers. So just the same way that I got 0.1593 there, I could have gotten it the same way by subtracting 0 and 1. The only 2 things that don't satisfy this. And that would have been a little bit more efficient of a way to do it. Alright? Because it's only 2 things to subtract rather than 4 things to add. But either way would have got us the same thing. Just how do we go about doing that? Alright, the other thing that would to do this for us is the CDF. When we see things, find the probability more than one. If it's not exactly equal to something, that's the job of the CDF. Alright, and the way that I do these CDF problems, let me delete this out of here, is I think of, alright, what is satisfying this event? These things are satisfying it. So I'm going to highlight those. Remember, the CDF always starts at 0 and and adds until you tell it to stop. So it starts at 0 and adds where you tell it to stop. Well, if I tell it to stop at 1, then I'll have the two other things that don't make up this probability. The only two things that don't. And I can subtract those from 1, and that'll leave me with this stuff that's in the yellow. That'll leave me with these 4 probabilities. So remember, the CDF starts at 0 and adds till you tell it to stop. So we could tell it to stop at 1 and then subtract that from 1. So what I mean by that is 1 minus the CDF, N is 5, P was 0.147, and where do we want you to stop? We want you to stop at 1. Right? We want you to go from 0 to 1. Stop there. We'll subtract that from 1, and that'll leave us with the other 4 numbers. Alright, again, what do we get? 0.15928. So to 4 decimal places, that rounds to 1.593. So any of those ways will work. So you don't have just one way to do it, but you need to come up with what works best for you. Alright, I would, if I were you, not go about the way that they want you to do it here. Alright, it's basically this method they're talking about right here is that second method I talked about, subtract. Right, they're adding all 4 of them up, but they're not showing you specifically how to do it. I would use your calculator and use any one of those 3 methods that we talked about. Alright, number 14. We have a brand name that has a 60% recognition rate. So that would be like something like Pepsi. You know, this is saying like 60% of the people know the brand name when they see it. Alright, if the owner of the brand wants to verify that rate, they want to start with a small sample of 10 customers. We want to find the probability exactly 6 of the 10 customers recognize the brand name, which would be 60%. Alright, so if that's true, we have, this is a binomial distribution because we know how many people we have. We have exactly 10. What's the probability that any one of these people will recognize the brand name? That's what this is. Right, 60% recognition rate, so 0.6. And then how many exactly are we looking for here? We're looking for exactly 6, so that's a PDF problem. And so we put in the 6 there and enter. So there's a roughly 25% chance that happens. All right, 0.251. All right, what's the probability the number who recognize the brand is not equal to 6? Remember, not 6 is 1 minus the probability it is 6. So we could find all the other probabilities and add them together, but remember, they all add to 1. We just found in the previous problem that that's the probability they exactly 6 do. So 0.7491, or to 3 places, 0.749, is the probability some other number occurs. Alright, so these are what we call complements, and complements always add to 1. So exactly 6, 0.251, not 6 or something other than 6, 1 minus 0.251 is 0.749. Alright, this one has multiple parts here, but it's similar to what we just did. Researchers wanted to conduct a study to determine if there were significant differences in graduation rates between medical students admitted through special programs and medical students admitted through the regular admissions criteria. It was found the graduation rate was 93% for medical students admitted through special programs. So we want to do A and B here. If 11 students from the special programs are randomly selected, find the probability at least 10 of them graduate. Alright, at least 10 is 10 or 11, alright, all 11. So I could say that I'm looking for the probability of 10 and I'm going to add to it the probability of 11. Right, that's at least 10. That's the only two numbers here that could satisfy 10. So the probability of 10 and the probability of 11 I could find on my calculator by doing the binomial PDF. Alright, 11 people are being selected. A 93%, 0.93, change it to a decimal. 93% graduation rate, and then 10, and then add to that the binomial PDF 11, comma, 0.93, comma, all 11 graduate, and hit enter. So 0.822 to 3 decimal places, 0.823. Now you could have done it separately. Like I could have, for instance, found the binomial PDF for 10, and then gone back and found the binomial PDF for 11. And then added those two numbers together. But again, you got to remember, this is a number, this is a number, so your calculator can handle it if you put a plus sign in between the two of them. All right, just got to remember to close that parentheses before you put the plus sign, or it's going to do something really funky there. All right, give you an error message too. All right, would it be unusual to randomly select 11 students from the special programs and get only 8 or fewer that graduate? 8 or fewer, that's again a CDF problem, but I could add it all up. Remember, this is 0 plus 1 plus 2 plus 3 plus 4 plus 5 plus 6 plus 7 plus 8. 8 or fewer, the things that satisfy that of the possible values are 0 all the way up to 8. So I could do what I just did. I could find the probability of 0 and then I could add to that 1, meaning 11.93, 1, and do this on and on and on and on all the way up to 8. Or I could remember that's the job of the binomial CDF. The CDF starts at 0 and goes until you tell it to stop. So 11, comma, 0.93, and I want you to stop at 8. Right, this is the probability of 8 or fewer that graduated. So 0.036, 037 to 3 places. So would it be unusual to randomly select 11 students and only 8 or fewer that graduate? So yes, definitely, because look at our number, 0.03, 3%, almost 4% chance of it happening. Yes, because the probability of this occurring is very small, right? Lower than that 0.05. All right, and then 16, I've started 16, I didn't finish it, but 16, this TV show recently had a 25 share, meaning that among the TV sets in use, 25% were tuned into that show. All right, usually, you know, it's very rare, like American Idol, or type the only shows that have numbers this good. But anyway, an advertiser wants to verify that share, so they've randomly selected 20 households with a TV set. Okay, so what's the probability that none were tuned to that if this is true, this 25 share? So that would be the binomial PDF. We selected 20 households. There's a 25% chance that they're watching this show, and none of them are actually watching, right? 0.003, that's where that number's coming from. All right, find the probability at least one household is tuned. Remember, at least one is 1 minus the probability of none. So 1 minus 0.003 is the 0.997. Alright, find the probability that at most one household is tuned to Lindsay and Tobias.